Hello, everyone, and thank you for joining us today. We're very excited to be hosting Dr. Mahdi Tavakoli, and we've been working with Dr. Tavakoli for quite some time, all the way back when he was doing his PhD research at the University of Western Ontario in London, Ontario, and obviously I've been working a lot with him as he's moved over. Where he currently is as in the Department of ECE at University of Alberta. He also directs the Telerobotic and Biorobotic Systems group there as well. So like I mentioned, he did receive his PhD from Western University in London, Canada, and was also a postdoctoral research associate at CSTAR, which is the Canadian Surgical Technologies and Advanced Robotics lab in London, Ontario as well. So we are very honored to have Dr. Tavakoli speak today and tell us all the wonderful things that he's been doing, him and his research group. And it's always been a privilege every time we visit his lab and see the type of work that his group does, especially, the ones we're extending to technologies and robotics and the medical field and helping all kinds of patients, especially children as well. So really looking forward to hearing Dr. Tavakoli give the presentation.
Well, thank you so much, Paul. Hello, everyone. It's my pleasure to be with you today, to be able to talk about my research. First of all, I'd like to thank Quanser for providing this opportunity to present. Quanser is truly a research-minded company, and it's been a pleasure to work with them. I have over the years always appreciated their willingness to help, be it with technical support, be it with various forms of support for my research, and I'm really grateful for all the help that they've provided. So today I'd like to talk to you about my research, specifically surgical and therapeutic and rehabilitation robotics. I'll be trying to frame this presentation in the context of issues that you face when doing hardware-software integration. But at the same time, I'll try to convey some more general messages about the area itself. So first, about Edmonton, this is basically one of the benefits of living in a cold environment. You get to see sunducks. This is what I captured on February 21st from my deck in my home. Basically, what you see is not a camera artifact. It's what you will see with bare eye. Basically, you'll see 3 suns. What happens is that due to the cold weather, ice crystals in the atmosphere reflect the sunlight, and so you see 3 suns. Same pond, same place. Later in the summer or spring, we get a lot of rainbows. So this is another cool thing about Edmonton that you have to be here to experience for yourself. Generally speaking, Alberta is a very beautiful place. I invite you to come over if you have not been here before. There are lots of conferences happening every year in Banff. And it's just it's a very scenic place. Really, the nature is beautiful, and you'll enjoy being in this environment. So please consider coming here, and if you are in Edmonton, please stop by in my lab and generally at the university to see what we are doing. So let me get into the talk itself. So the motivation for using robots in medicine comes from this sharp rise that you see in the fertility rate in women in the immediate period after the Second World War. This is what we call the generation of baby boomers who have now aged or over the age of 60, 65. They require healthcare, and that's putting a lot of burden on the healthcare system of Canada, but not just Canada. Many countries are having the same issue, basically the aging of population, which puts a lot of burden. Already the wait times for surgeries, therapies, and even imaging services are long, and this is just going to get worse. So the solution here is to use robots to alleviate this burden. But we have to properly define what medical robots are and what their roles are. robots are not here to replace surgeons. That's my main theme today. They are actually tools that are driven by information, for instance, by images, smart tools in the hands of surgeons and therapists. They're there to extend their capabilities, not to replace them. It's very important. So robots for medicine are defined as tools that can couple complex information to physical action in ways that human can't. They can exploit the complementary strength of humans and machine, and also they will enable treating patients with enhanced safety and efficacy. So this is the general definition. Now, if you look at the state of the art in the clinic, most of the time, everything is done fully manually. There is no automation happening. The other end of the spectrum would be to fully automate the entire job of the clinician and leave nothing for the clinician to do. But this is not really what we are after. So on the right-hand side, I've listed what a clinician would do versus what the machine would do. In the fully manual case, everything is done by the machine, by the human, and there's nothing for the machine to do, so you don't benefit from the machine. And in the automation level 3, everything is done by the machine. There's nothing left for the human to do, which is not really desirable. There are going to be serious problems with clinical acceptability of the technology if it excludes the clinician totally from the clinic. There are going to be concerns about safety. Even patients won't like that. So what we are interested in are these intermediate levels of automation. For instance, automation level 2 or semi-autonomy, where some tasks that are safety critical and that really require the expertise of a clinician are done by the clinician, but other things that either have a supporting role or are computationally expensive operations and they require algorithmic work are done by the machine. This is the best split of the work. So in this context, I'll talk about these areas and basically what we have done on them. I'll talk about haptic interaction, and I'll talk about redundant haptic interfaces we are designing, haptic teleoperation, and beating heart surgery, which was done with haptic teleoperation, and so forth. So I've ordered them according to increasing complexity of hardware-software integration. But again, another theme here in this talk is about human-machine collaboration. And the ones that I have marked, haptic teleoperation, image-guided robot control, the ultrasound scanning of the breast, and rehabilitation of people with disability, these are things that I'll try to tie into this general theme of human-machine collaboration. So let me get started with haptic interaction. We are working on redundant haptic interfaces. So as you may know, there are design trade-offs between desirable characteristics of haptic interfaces. For instance, you want to have big force feedback capacity, which means you will have to have big motors or actuators on your haptic device. Well, that will increase inertia. And so the apparent inertia at the end effect of the haptic interface will be big, which is not good. So this is a contradiction and a conflict that you have to resolve and strike a trade-off somewhere. Or if you want to have a big workspace size, then the link length have to be large, which means that the mechanical stiffness will go down, but you want high mechanical stiffness out of a haptic device. So there are these conflicting requirements. To best address these requirements, we've started working on redundant haptic interfaces, basically haptic interfaces that have more degrees of freedom than minimally required. For instance, in the 3D space, you need a maximum of 6 degrees of freedom for XYZ role PGR motions. What if you have a 7 degree of freedom robot haptic interface or an 8 degree of freedom haptic interface? Well, in this case, it's possible to have the same end effector position and orientation, but various configurations for joints. And this allows for optimizing these desirable characteristics further than is possible in a non-redundant haptic interface. So compared to non-redundant haptic interfaces, redundant haptic interfaces have some intrinsic advantages, which means without any controller, you get bigger workspace, you get reduced apparent inertia, and increased manipulability. Now, you can also implement a task space impedance controller on the redundant haptic interface so that you have a desired impedance or apparent inertia seen at the end effector of the haptic interface. You basically want to lower the inertia that the user feels when moving the haptic interface. So this is that. And then because you have this redundancy, you can implement null space control, which manipulates the joint motions without affecting the end effector pose. And this null space control can further reduce some of those characteristics, for instance, the apparent inertia, or can increase the manipulability. If you're interested, you can look at these papers that we have published. So here's an example. At the base, you have a 2 degree of freedom haptic interface from Quanser. It's what we call in this presentation the rehabilitation robot, because we use it for rehabilitation purposes. What you see at the end effector of this Quanser 2 degree of freedom robot is 2 more degrees of freedom coming from a Phantom 1.5A. So we've taken the base of the Phantom out, and we have put the last 2 links of the Phantom on its side. So you end up with a 4 degree of freedom haptic interface that implements planar motion. So for 2D, this is a redundant haptic interface. We saw in some psychophysical experiments that using this haptic interface compared to, for instance, just the rehab robot itself, users are able to discriminate between changes in the force that are smaller. So what is called the just noticeable difference in force perception will improve when you have a redundant haptic interface compared to a non-redundant haptic interface. So this is some of the result. If you look at this just noticeable difference values, these are the means of just noticeable differences. The smaller, the better. You see that the redundant haptic interface is able to lead to a much smaller just noticeable difference compared to, for instance, the rehab robot alone. Now, I'd like to talk about hardware-software integration too. So I'll have these diagrams for the experimental setups that we have implemented, so that you are also familiarized with the issues that are involved when you want to build such a system. Both the redundant haptic interface, both the rehab robot of Quanser and the Phantom 1.5A are supported by the software provided by Quanser called Quark, which is basically a Simulink toolbox for real-time control of these haptic interfaces and some other devices. Now, these devices, the rehab robot and the Phantom 1.5A, are connected either through parallel port or through USB port to a PC. So there is proprietary communication going back and forth in terms of positions are sent to this PC from the 2 devices, and then torque commands are sent back. That's how we do control. Now, because we want to do task space impedance control of the end effector, we have to also have this force sensor measurements sent to the same PC. And this is when it gets interesting. So to be able to send it to the same PC, what we have done is we have connected the force sensor to a PC, and then we have done UDP transmission of force data from this computer to the control computer. So this is something that you will see over and over through this presentation. We use UDP a lot when we are trying to distribute the computations, or we are trying to transmit data between different machines for various reasons. So all these dashed dot lines are UDP communication. Moving on to the second topic, I'd like to talk about our research on haptic teleoperation, and specifically I'll talk about beating heart surgery. So currently the way surgery is done is surgeons just stop the heart before doing anything complex on it. They put the patient on a heart-lung machine, which is basically an artificial heart for the duration of the surgery, which oxygenates the blood and circulates it through the body. But there are side effects and risks associated with using a heart-lung machine. Sometimes surgeons just locally stabilize the heart without stopping it using a heart stabilizer, basically just something to fix the heart down. But the problem is that you can't do all sort of heart operations using this approach. So really, can we operate on the heart without stopping it? Well, it's possible if, sorry, I have a problem with running this video, just 1 second. All right, so consider on the right-hand side, this pilot trying to land the helicopter on the deck of this ship in choppy waters. This is very difficult and risky operation. As the helicopter is coming down, the ship can come up and collide with the helicopter and destroy everything. So this is really what a surgeon is dealing with when trying to operate on the fast-moving tissue of the heart. So I've written here the maximum velocity of the heart, the maximum acceleration of the heart. They are really high, and the heart actually jumps by about 10 to 15 millimeters in no time right after contraction. This is very difficult. So we are interested in seeing if we can do these two operations, like an extracardiac procedure on the outside of the heart called pericardial synthesis, or we could do some intracardiac procedure, namely mitral valve repair. To be able to do this, what we need is a robot that synchronizes its motions to the motion of the heart, even when the surgeon is not doing anything. So what we need, first of all, is an image sensor like ultrasound to be able to see through blood, to be able to see through tissue, and visualize the surgical instrument that's attached to the robot as a line, for instance, in this ultrasound image, and also see the closest heart tissue and find the distance between them. Then you need to have some sort of collaboration between the machine and the robot. Some of the jobs should be done by the machine automatically without the intervention of the surgeon. That's this part. The machine has to automatically synchronize its motions, or the motion of the tip of the surgical instrument, to the motion of the heart. It has to go up and down with the heart even when the surgeon is not doing anything. Then the surgeon will have to manually control the distance between the tip of the surgical instrument and the heart tissue. If we can do this, then we have really achieved some sort of motion compensation, and the surgeon would have the feeling of operating on an arrested heart, even though the heart is actually beating. Now, the surgeon has to manually control the distance between the robot and the heart through something, and that's a user interface. And so this user interface, manipulated by the surgeon, will basically add motions to the motions of the robot coming from step 1. There are some issues in this scheme. I mentioned that you have to use ultrasound images. Well, by the time you acquire ultrasound images, bring them in real time to a computer, process them, find where the needle is or where the instrument is, and where the heart tissue is, time will have passed, about 200 to 300 milliseconds, depending on how fast you can do the operation. This is a big duration considering how fast the heart motions are. So what you need to have is some sort of predictive control to be able to predict when the heart will be 200 or 300 milliseconds from now, and then send the instrument there, basically working based on old data, because you have to do image processing and acquisition that takes time. So the first issue is the delayed measurement and the need for predictive control. The second problem is this is a multi-rate system. Your control system, your control loop has to run at a fast rate, whereas the ultrasound images, which is basically the feedback path, come at a much lower rate. The other issue is that the motions of the heart itself are unknown. The heart motion changes from one beat to the next. And you need precise tracking, less than 2 millimeters of error. So here is just a block diagram really showing in a very simple way how this problem can be tackled. So you measure the heart motion, basically the motion of the point of interest on the heart. This is coming from ultrasound images, therefore it's delayed, and it also has a slow sampling rate. So first of all, you have to upsample it, and then you have to predict using something like Kalman filter. If you're interested, please see the papers at the bottom of the page. So we upsample the heart motion and we predict it into the future, and then we feed it to this control loop that you see here. So as you see, the addition of the heart position and the surgeon's position together becomes the desired position for the robot. So the robot position, in the best case, if the control loop works as desired, will become equal to surgeon's position plus heart position, which means that the robot to heart position will be the surgeon's position. This means that the surgeon is really controlling the distance between the robot and the heart, and that's what we wanted to do previously. So let me show you some experimental results. First, let me explain what these two procedures are. The first one is pericardial synthesis. It's basically buildup of fluid in the pericardial sac around the heart. So there's a sac of fluid around the heart, and you have to drain this fluid. The way it's done is while the patient is awake, a needle is inserted between the rib cage, and then this needle has to go into this pericardial sac but not go into the heart. If it goes into the heart, then you require emergency open surgery. So you have to stop short of the heart, not puncture any of these coronary vessels, not puncture the heart. You have to stop there. And then a guide wire is inserted through the needle is retracted, a tube to drain the fluid is inserted over the guide wire, and then you basically drain. But you can imagine how stressful this would be on the cardiologist doing it. If the patient who is awake and is sick, for instance, coughs, the chest will come up and the needle will go further into the body, puncturing the heart. So this is one operation that I'll talk about. The other one is annuloplasty for mitral valve repair. The way a normal heart works is that fresh blood comes from the lung and pours into the left ventricle. Then the heart pumps, which means that the ventricle contracts. This results in fresh blood going to various body organs. So the function of the mitral valve is to close. Basically, there are two leaflets. These leaflets are supposed to reach each other and form a seal so that the fresh blood that just came from the lung does not go back to the lung. In some patients who have mitral valve regurgitation, or just called leaky mitral valve, what happens is that these two leaflets are farther apart than what they should be. Therefore, they don't form a seal, and some of the blood escapes back to the lung. This reduces the efficiency of the heart and makes the heart work harder. One way to solve this is annuloplasty. The way annuloplasty works is that the heart is accessed from the top. So this is the top view. These are the two leaflets of the mitral valve that are farther apart than what they should be. A ring like this is brought in from the top and stapled on the annulus of the mitral valve. Then there is a pull cord going through this ring. That cord is pulled, resulting in a reduced circumference for the ring and for the mitral valve. Therefore, the two leaflets get closer to each other and hopefully they'll form a seal. So this basically comes down to a staple insertion. Now, as far as the pericardial synthesis, this is the experiments that we have performed. So this is a mechanical heart simulator. This is a simulated pericardial sac. This is our surgical robot with some optical markers to know where the surgical instrument and the heart is. This is the user's console, and this is the drainage mechanism. So without motion compensation, the surgeon has to move the master robot such that the slave moves in synchrony with the heart and at the same time try to compensate, which is very difficult. But with compensation, the hand is steady and you just control the distance between the tip of the needle and the pericardial sac, and it becomes much easier to withdraw the fluid. For the second case, which was annuloplasty, this is the experimental setup. It's basically a water tank. This is the same heart simulator. There is some tissue here simulating the heart. This is the ultrasound probe giving us these images here. This is the surgical instrument connected to the slave robot, which you see here as a line, and this is basically the heart. This is the user interface for the surgeon, and this is the mechanism for staple insertion. So now see what happens with motion compensation and without motion compensation. First, without motion compensation. So without motion compensation, the surgeon has to move the instrument up and down in synchrony with the heart based on what is seen in ultrasound images and try to deploy the staple. This is very difficult. It's almost impossible to do. What people do really, they wait at the top for the tissue to come up to them to deploy the staple. You may be able to deploy the staple once, but you can't do the whole operation this way. But with motion compensation, what happens is that the instrument goes up and down automatically, regardless of what the surgeon is doing. And the surgeon can only control the distance between the tip of that instrument and the tissue. And this way, it's much easier to deploy the staple. So this is an example of a correctly deployed staple. This is actually the tissue. I don't know if you see it well or not, but the staple has been deployed correctly and is anchored in tissue. We have continued working on this system by incorporating haptic feedback for the human operator. In the previous 2 slides, there was no haptic feedback for the human operator on the master robot. The way we have done it is through some generic impedance surfaces defined for the motion of the master robot and the slave robot. Really, all you need to know here is that the force applied by the human on the master robot and the force applied by the heart on the slave robot are both measured by force sensors. They are fed into these 2 impedance surfaces. Desired positions for the master robot and the slave robot are calculated, and then those are executed through some position controllers for the master and the slave robots. This way, we are able to achieve both motion compensation and force feedback for the human operator by properly choosing the values for this mass, spring, and damper coefficients, depending on the frequency of the heart rate. So this is what you see. Again, the hand is steady, and the instrument is moving automatically with the heart, and the surgeon just needs to look at this and deploy the staple correctly. So this is a diagram of how we have done the hardware-software integration. What is interesting here, beside the fact that, again, we have the rehab robot and the phantom robot, which talk to a Quark PC, is the fact that whereas we had to use a PC connected to the JR3 force sensor to send the force measurements through UDP to the controller PC, we had an ATI gamma net for sensor that directly sends UDP information to the controller PC. So no more PC is required for that force sensor. Moving on, I'd like to talk about image-guided robot control. Specifically, I'd like to talk about prostate brachytherapy. So prostate brachytherapy is a procedure for treating prostate cancer where very long and thin needles, about 1 millimeter in diameter, that are hollow and preloaded with radioactive seeds, are inserted into the prostate, and those seeds are deposited into the prostate in order to kill the cancer. So the accuracy of the procedure and the side effect profile really depend on the accuracy of seed placement. To be able to achieve this operation, you need some sort of imaging. So a transrectal ultrasound probe is inserted into the rectum, and it gives you sagittal images and axial images like that. So this is the operation being done manually at the Cross Cancer Institute in Edmonton. This is between the leg. The needle is inserted. The surgeon views the needle path under ultrasound images coming from this ultrasound probe inserted into the rectum, once the needle is determined to be in approximately the right location and at the right depth, then through this mechanism that you see here, they deposit the radioactive seeds within the tumor or around the tumor in the prostate to hopefully kill the cancer. This is the best case. Now I'd like to talk to you about how this operation is planned. You should have seen this block diagram in Taylor's paper in 2003. You first have to preoperatively plan the operation. Once you go into the operating room, you have to update the plan because nothing will be really exactly according to the plan. You have to update it based on an updated model. You have to do some part of the operation and continue this loop until the whole procedure is completed. So I'd like to talk to you in this context about prostate brachytherapy. So before the operation, about 2 weeks before the day of the operation, this patient goes into the operating room without any needle insertion. The probe is inserted into the rectum and a bunch of axial images are acquired, and the prostate is delineated by an expert surgeon in each of those. So you have basically a 3D map of the prostate. Then they come up with a dosimetry. Basically, they through some optimization algorithm, they determine how many needles they have to insert, in what locations they have to insert them, what should be the distribution of seeds within each needle, and to what depth each needle should be inserted. This is for the best case, assuming that needles will go on a straight line, but actually they don't. So as you will see in the movie on the right, this is an experiment. When you insert these brachytherapy needles, they tend to bend. That's really inevitable. And the reason for it is that to be able to cut tissue, these needles are beveled, which means that there is an imbalance of force at the tip, which means that as they are inserted, they tend to bend in one direction or the other. For instance, in this case, this needle wants to bend down. If you rotate it around its main axis by 180 degrees, it will tend to bend upright. And that's really our control input. What we'll do is, when inserting the needle, if we are able to observe the needle deflection through ultrasound images, then we can just rotate the needle in the simplest case to be able to correct the needle path. So this is a video that shows that through needle rotations that you will see here, it's possible to keep this needle that tends to bend on a straight path. Here the tissue was transparent, so we just use the camera, but in the patient we have to use ultrasound images. We have discussed in the paper, you see at the bottom of the page, how this is a control loop. I won't go into the detail of that, but if you're interested, please look at that paper. We have talked about how the needle tissue system should be modeled, what sensors are needed. You need observers, you need trajectory planners and trajectory predictors due to the non-holonomic constraints of needles, and you need to design various controllers for different objectives. So I won't go into that. But what I'd like to discuss here is, okay, in this block diagram, what is the role of the surgeon? What does the surgeon do? Nothing. And that creates problems. Surgeons won't like this, and patients won't like this. So, for instance, we are delegating even the needle insertion to the machine, which creates all sorts of safety issues in case the system goes unstable, for instance, and again, clinical acceptability issues. What we decided to do, and really our brachytherapists and people we've talked to really like it, is to split the job, delegate the computationally expensive parts of the operation, which is the control loop itself, because you have to act on images, you have to act on sensors and so many other things, to the machine. Therefore, the needle rotation is decided by the machine on an automatic basis, while the surgeon is in charge of inserting the needles. So this really puts us in this hierarchy of automation here, in semi-autonomy, where insertion is done by the surgeon and rotation, which is difficult to compute, is done by the machine. This is a system that we have filed a patent on. It's basically just a handheld device that's actuated and instrumented and informed by ultrasound images, and the surgeon allows the surgeon to insert needles while rotating it automatically as needed. So as you see here, the surgeon inserts the needle, and the machine does the rotations based on path planning algorithms that work in the background that are themselves informed by all sorts of sensors and ultrasound images. Now, as one example, this is one controller that we have implemented. So here, the input to the controller is the position of the needle base and the depth of needle insertion, which is in the hand of the surgeon. The output from the controller is, okay, how much should the needle base now rotate? This also needs to be informed by ultrasound images of where the needle tip is. Therefore, this is the signal flow diagram that you end up having. The needle steering device is connected to a DAC. This is basically controlled by a target machine. On the host machine, you have all the control computations happening. So what has to happen is through UDP, we send the needle base position data to this computer, and it sends back the needle base desired position data, or how it should move now. And this is informed by ultrasound images. So we have another PC to be able to distribute the computation, because you can't do all of these on one machine for real-time control constraints. So we have to use a frame grabber to capture the screen through HDMI, and then this frame grabber is connected to a PC through USB, and then this PC here does all sort of image processing to calculate the location of the needle, and then send that through UDP to the real-time control computers. Moving on, I'd like to talk about what we have done for removing X-ray from breast imaging to diagnose breast cancer. This is a case of robot impedance control. So breast cancer is the most commonly diagnosed cancer in females. Typically, X-ray or mammography is used for diagnosing breast cancer. And the way it's done is that there are these two plates. The breast is compressed between the two plates, and an X-ray image is obtained. Well, there are issues with this. First of all, you are exposing the patient to ionizing radiations, and you are also exposing the clinician to radiation. There's also tissue compression. So because of this, the two compression plates. Later, if you diagnose a cancer, that has to be taken out through surgery. So exactly where in the undeformed breast is the cancer? That's a question that we can't answer using mammography. Turns out that standard 2D ultrasound images can actually find the tumor in the breast and can even differentiate between different types of the tumor. Therefore, we saw this again as an opportunity to bring the clinician and a robot together. So the clinician will manually move the ultrasound probe as he or she wishes on the surface of the breast. And the job of the machine or the robot is to automatically control the forces applied by the probe on the breast tissue for minimum deformation. So there are some systems that work based on ultrasound imaging. They're called ABVS, but they also deform the breast just like mammography, and therefore they are not good for interventional purposes. So I'll probably skip the details. I'll just show you a video of how this is done. As you see, the user is able to tangentially move the ultrasound probe pretty freely, while the robot controls the perpendicular force applied by the probe on tissue for best image quality and minimum tissue deformation. So this is again a case of impedance control. Here we have this Motoman robot used. Now the Motoman robot comes with basically a Windows computer that has two cores, a Windows CE for real-time control and a Windows 7 for just writing your control loops and codes. So what we have done is we have interfaced even this Motoman to a Quark PC for easier control, because then we will be doing everything from Simulink, and that's easier to debug and prototype. What we have done is we have sent all sort of information, for instance, the robot position data that's captured by this low-level Motoman controller PC through UDP to the Quark PC, and sent back the commands, for instance, the velocity command for the robot back to the other motoman driver. Again, because of impedance control, we need to read the force sensor. The gamma net force sensor goes directly through UDP to the Quark PC without the need for another PC. And we need to also capture ultrasound images, but this is purely for data logging purposes. It's not being used in control right now, but we intend to do it in the future. Moving on, I'd like to talk about rehabilitation of injured workers and how haptic virtual fixtures and augmented reality are used. So people who are injured on the factory floor require what's called functional capacity evaluation, basically figuring out how much weight they can lift, how far they can carry it, and stuff like that. So that's very subjective assessment. In terms of rehabilitation and assessment, if you go to one of the clinics that they have big spaces like a gym with all sort of work-related hardware. So all work environment are physically simulated to be able to assess the status of an injured worker and rehabilitate them over time. You can imagine that this is very expensive in terms of space and in terms of hardware cost. Also, patients or these injured workers can become uncooperative, unmotivated, or bored. What we have tried to do is to replace this physical hardware with one unified robotic system that's aided by an augmented reality display, such that we can simulate all work-related tasks in one setup, with one setup. Just like a flight simulator, where you have the dynamics of the aircraft replicated and presented to you through the yoke and all the other handles and levers. And there is a virtual reality display to show you basically what this pilot would see. Here, we will have a simulator that creates the virtual environment and superimposes it on the workspace of the user to an augmented reality display that I'll talk about in a second. And then you have haptic virtual fixtures that create the dynamics of the actual physical task. So what we have here at the top is a projector hanging from the ceiling and pointing downward. When projected on this curved screen, it is possible to create 3D pop-up illusions of actual of objects in 3D. Of course, the user has to wear shutter glasses. The robot will be impedance controlled to move in all directions, but then you can create whatever environment you want. For instance, we want to create the experience of using a physical paint roller to paint a wall without having a wall, without having a roller. So this is what we have done. A haptic virtual fixture is used to create a wall about here. So from the perspective of the user, a wall is felt haptically. And also this roller appears at the end effector of the robot, and you basically see a wall being painted. This reduces the need or eliminates the need for having a physical system in place. I'm just trying to go a little faster to be able to make it on time. We have recently used the same idea for rehabilitation of people with disability. What we have done is, again, using the idea of augmented reality, using projection mapping, we have co-located the workspace for the user in terms of visual space and motor space. There is no disconnect anymore when you're using a system like this to play a game between what you feel and what you see. So again, the Quanser rehab robot used for playing this car driving game. This is a haptic game, so when you get behind the car, you actually feel it. And note that you see it in the same location. This is projected from the top. For 3D, we have also done this. Again, 3D is just turned off for the purpose of this video, but the user really feels everything in 3D. So there are some tasks that we have developed here. For instance, this is a point snapping task in 3D that's haptic. So you go between points and you are attracted to them and you feel those points. Or this is a task of catching a ball which is again a haptic task and with 3D augmented reality. The last topic I'd like to talk to you about, or the second last topic, is learning from demonstration for rehabilitation of people with disability. So there is a need to rehabilitate people who have suffered, for instance, from a stroke through repetitive exercises. These repetitive exercises require the intervention of a therapist in a hands-on way, which can be very physically demanding on therapists. Imagine you want to do this 8 hours a day. So robots have been used to replace a therapist, but probably that's not the best idea. What happens here is that although the robot has no fatigue and has high accuracy, what happens is that the therapist is kind of excluded from the loop and can only intervene through the computer, a mouse and a keyboard. Also, the tasks that are defined are very narrowly defined tasks, mostly reaching motions. We are interested in enabling patients to engage in activities of daily living, like taking a spoon to eat, or bathing, or dressing, and all other activities of daily living. These are much less certain in terms of modeling and coding. They happen in unstructured environments, and therefore it's very difficult to actually code them and pre-program a robot for them. But what we can do is to rely on a human to kinesthetically teach a robot how to perform that task. So this is what we have done, and I'll show you one of these again in the interest of time. Consider this block diagram. Assume that you have a patient who has problem clearing his left toe. So when walking, he cannot clear his left toe and therefore does not walk. To be able to benefit from walking, for instance, better blood flow and circulation, a therapist would have to lift the left side of the patient in the correct part of each gait cycle and do it for, let's say, an hour. This could be very difficult for a physiotherapist to do. What you can do is to have a robot lift the left side of the patient up when needed. But you have to teach this robot how to do it. So this is what we have done using these learning from demonstration schemes, and I'll directly jump into the slide that has that. So as you see here, a therapist on the left is pulling a robot that's through this pulley and rope mechanism is hoisting the left side of the patient up in the correct part of the gait cycle. Now, in the absence of the therapist, the robot is completing the same task even when the therapist is absent, so that the patient can continue this exercise for a long time, for instance, for 1 hour, and benefit from it without taking up the therapist's time. Now, I'll just show you this signal flow diagram. Again, you have a case of impedance control. The only difference is that you also have to have a motion tracker to keep track of the gait, and that requires basically, again, some UDP communication between a PC to the control PC. We have applied the same idea to assistive technologies for children. So children who are with disability require opportunities for play. For instance, a child needs to be able to play this hot wire game regardless of the physical disability that deprives him of the chances to play that. Can you do this? Yes. What you need is a helper to come in and help a child. This is a simulated child with disability. Help a child perform that task without error. Then, in the absence of the helper, the robot will kick in and compensate for the absence of the helper and deliver the same sort of help that the helper was providing. So this is a video of that. So a helper is helping the child go, for instance, between these 2 points and these 2 points. This is the simulation of that hot wire game in 2D. So we need a few iterations of this basically demonstrations of how the task should be done. Then Gaussian mixture models are built, telling basically how the therapist plus the child together, or the helper plus the child together, perform. In the absence of the helper, the robot will see that there is a deficiency and will step in and compensate for that deficiency so that the child can have opportunities for play. This is important for social engagement of children. So in the interest of time, and to leave basically some time for questions, I'll talk about one last topic, which is integration of our hardware and software into ROS, and then I'll stop for questions. If you have any questions about the slides that I didn't show, I'm very happy to talk about it. So we started probably a year ago to try to bring all of our hardware into a common framework to be able to streamline the integration and communication between hardware components. For this, we decided to go with the robot operating system because it provides high-level messaging, low-level device control, hardware abstraction, in the sense that it becomes a device-independent way of programming devices. If you change a haptic device, for instance, you don't have to reprogram everything again. You just have to tell in one line that this is a different haptic device. Now, we've noticed that Peter Kazantzidis at Johns Hopkins has started something very interesting that anyone who is interested or is encouraged to look at. It's called Collaborative Robotics Toolkit. Basically, it's some abstraction over an abstraction. It works on top of ROS if needed, and it creates a language for collaborative and medical robotics research. So we have done some developments. For instance, we have through UDP integration mainly, we have adapted our Quark devices to ROS platform. We have done some updates to current drivers, and we have made most of it available on GitHub if anyone is interested. I just want to show you two more slides about how we have configured under ROS now. So consider this Quanser robot on the left-hand side, Quanser HD squared. It talks to Quark natively. Then what we have done is through UDP, we have created a UDP interface to be able to send the information coming from this HD squared robot to another robot that works under ROS. So that's what we have done to be able to, for instance, teleoperate this Motoman robot from an HD squared. Another example is admittance control, where we have again used a JR3, for instance, for sensor for impedance control. It's connected to a PC. That PC talks through a ROS topic to some other device that's under ROS, for instance. So to conclude, we had to move, as I'm sure you appreciate by now, we had to move between various hardware and software configurations for different applications. We had to rely heavily, very heavily, on UDP communication. And this has several reasons. Sometimes we do master-slave teleoperation. Of course, there the master and the slave are not in the same location necessarily. You need to have some sort of communication, and UDP is the best. Sometimes for distribution of computation, we had to rely on UDP. So we put the force sensor on one machine, and that machine sent UDP. We put image processing and the frame grabber on one machine, and that machine outputted something through UDP, and all other sort of control-related constraints led us to distribute the computation and use UDP a lot. Sometimes our sensors output UDP natively, like the gamma net sensor from ATI that I talked about. This creates a high level of complexity in the system because of just the variety of devices that we deal with. We deal with robots, haptic interfaces, ultrasound scanners, possibly other medical imagers in the future, motion tracker, Kinect, force sensor, and you name it. There are so many different things going on in these systems. Now, putting this hardware-software integration issues aside, just general conclusions, I'd like to emphasize that there is a plethora of potentials in robotics-assisted medicine. It's very exciting that there are so many possibilities. If anyone here is a graduate student who's looking for a project, I really encourage them to look at the various problems that people are studying in the field. You will find a lot of things to improve upon. The goal really should not be to replace the surgeon or the therapist, our goal should be to extend their capabilities. This is best done through cooperative control or through teleoperation control, where the user is directly involved, or through learning from demonstration paradigm, where the user is involved for part of the intervention and then leaves, just for time saving and cost saving purposes. Robots can make surgeries and therapies more accurate. They can make them more safe with less trauma and side effects. And there are other possible advantages. For instance, entire new treatment options can become possible when you start using robots. For instance, if beating heart surgery becomes possible, then this is completely new because currently it's not being done. There could be saving on operating room times and costs, and because you're using a robot and a computerized system around it, everything is logged. There is excellent documentation for follow-up and assessment purposes. So I'd like to thank all the current and past graduate students and postdoc who contribute to this. I'd like to thank all the collaborators, whom I can't name here because there are just too many. I'd like to thank all the funders. And last but not least, I'd like to especially thank Quanser for all the support that they've been giving us, and it's been an excellent partnership. Thank you so much, everyone. My apologies for taking a little bit longer than I was scheduled to. I'll be very happy to answer any question that you have.
Thank you, Mahdi. Thank you, Dr. Tavakoli, and it was exciting to see all the great work that you have done, and a lot of it that I was aware of, and a lot more that I wasn't. I mean, it's tremendous what you've been able to achieve out of the lab in Alberta. So thank you again for your presentation. So we do have some questions. So I'll start from the beginning. So from Amir, he's asking, hi, Dr. Tavakoli, what strategy would you suggest for synchronization between, force sensor, a phantom device, a Quanser robot, given that all of these systems have different sampling frequencies?
Right. So what we have done in the lab has, as I said, has always relied on UDP. And what we do is try to send data as fast as you can through UDP. And then in the best case, you will have more data than required, so you can dispose of some of the older data that has come up, that has arrived in one sampling time of your control loop. That's the best case. And usually we have found that there is no problem really doing this. So just send data through UDP as fast as you can, and then do the control as fast as you can, as fast as the system allows and as fast as the sensors allow it. So for force sensor, I'm not too worried about. If you are talking about other sensors, then you have to think about upsampling. So for instance, ultrasound or motion trackers or other sensors, they may be working, for instance, at 50 hertz, 60 hertz, while your control loop is running at 1 kilohertz. In that case, you have to do upsampling, which creates some delay. So you have to think about how you want to do the upsampling. If you want to do a good upsampling, you need to consider, for instance, about 12 points to the last 12 points that you have received, and do a curve fit to those 12 points to be able to interpolate them for upsampling. But that causes a delay of up to 12 points. So you have to be able to combat the time delay separately, which is again not a big issue. For instance, if you have teleoperation, in teleoperation you have time delay anyways, and therefore a little bit of more time delay for caused by upsampling isn't the biggest issue, but it really depends on the application. So that's what I can say at this point.
Okay, thank you. So we have another question. From Angela, I believe. Thank you for your presentation. Very interesting so far. He's asking, the methods for motion compensation are on a simulated setup. What are, in your experience, the obstacles in reaching implementation in surgical robots and testing on human subjects?
The way we have done motion compensation, so let me elaborate a little bit on how we have done motion compensation for physiological organ motion. So what happened in our case was that we had the heart that's beating. So we are fortunate that for the heart, you can assume a pseudo periodic model, like a quasi-periodic sinusoidal, basically sum of sinusoids model for the heart. with some unknown coefficients to be determined. Then we were able to transfer this, and the details are in the papers. If you're interested, look at the papers written by my former student Megan Bowthorpe. So she turned that basically Fourier series, which is some sinusoid, into a state space representation which was appropriate for Kalman filtering and prediction. So again, in this very particular case, because the motion of the heart we know is periodic or semi-periodic, if not exactly periodic, we were able to have a Kalman filter formulation to be able to capture that motion and predict it. That's what we did. For things like respiration, I think that you can do the same thing pretty much. It's probably even easier because the frequency of respiration is lower. The magnitudes are higher for the motion, but the frequency is lower compared to heartbeat. So it should be easier, given the right type of sensor and measurement, to be able to predict, to be able to capture the respiratory motion and to be able to predict it in the future based on the model that you have captured. For other types, I would say depends on the exact application, what you want to do. One other thing that I'd like to add is, for heart, for instance, we are able to, although we have never done it, but it's possible to inject drugs into the patient to kind of slow the heart rate, to slow it and make it consistent for the duration of the operation, to make it more consistent and more predictable. It's also possible, for instance, to put a pacemaker on the heart to force it to beat at the exact, according to an exact timing dictated by the device. So there are these tricks, but again, it depends really on the application that you have in mind.
So another question we have is more ROS related. So is ROS compliant with any regulations or medical software certifications? Basically asking, can ROS be used, or do you know of any examples where ROS is in the use case that has been approved by FDA or EU regulatory bodies?
So, ROS was developed really for industrial applications. So ROS industrial, really, that's been the main purpose. ROS has not been developed originally for medical applications. And this is why that collaborative robotics toolkit movement is taking off, led by Peter Kazantzidis, because really ROS isn't meant for medical applications. So we are not aware of cases that have been approved for medical use by FDA, for instance, that are working under ROS. And possibly ROS isn't really the ideal framework for that either. That CRTK has better chances of being able to do that.
So maybe one final question, which is interesting as well. So you were mentioning a lot of these imaging data, position feedback of some of these organs was coming through image processing, which is great, but also has slower rates and some more computation in the loop. Do you see any improvements in that by using things like MEMS and IMU, sensors to speed up and better synchronize that motion or estimate that motion?
Yes, that's an excellent question. So possibly, but not always. For instance, consider the case of prostate brachytherapy. You have a needle that's 1 millimeter in diameter. You can't put any sensor on that needle because you want to insert it into tissue. It's going to cut tissue. It's going to injure the tissue, even if you solve all the sterility problems. You can't put any sensor within the needle either, because that's a channel you require for delivering radioactive seeds to the prostate. So really, we are stuck. There is no way to put a sensor on the needle. What we've done is, Thomas Lehman was my former PhD student who worked on this. We put a force torque sensor at the base of the needle, And we try to do kind of sensor substitution, in the sense that instead of having an imager capture the needle deflection, use the information coming from the force torque sensor in 6 degrees of freedom and a mathematical model relating those force torque sensors at the base and the needle tip deflection to the tip deflection. So basically, we eliminated the need for ultrasound in that case by putting a force sensor but outside the patient's body, and then using a mathematical model to relate the measurement of that sensor to the quantity that we are after. So this is possible in some cases, but it's not perfect. Really, at the end of the day, you have to rely on images, because you will need to know not just how the needle is deflecting, you will also need to know how the tissue is deforming, the prostate, for instance, is deforming, etc. So we have heavy reliance on ultrasound imaging at this point. Yes, that's what I would say. Something that we can do, for instance, in the case of beating heart, we could use ECG signals, for instance, to have to rely less on ultrasound. Basically, have more information coming from the electrical signals of the heart, so that we can predict its motion without much reliance on ultrasound images. Or things like EMG for other applications. So it's possible to kind of have some sort of sensor fusion to rely the dependence on ultrasound images, but still we really need them for most of the applications, as far as I can see.
Okay, well, thank you very much, Dr. Tavakoli, and thank you for everybody for asking such engaging questions and then participating in this webinar. It's always our pleasure to facilitate this exchange between the community of our users and people doing some amazing research, especially when it's all for the betterment of society and advancement of the technology. So. Thank you again to Dr. Tavakoli, who's been a longtime friend of Quanser's, and thank you for everyone else for attending and engaging with us on the webinar. And we will be emailing you all the information pertaining to the webinar, where you can download some of the slides and put you in contact if required.
Thank you, everyone. Thank you, Paul. Thank you, Susanna. Have a great day.